Hello, in this video we are going over waves, all of waves, core and HL. We're going to try to go through a little bit of everything. Okay, take this for what it is. Waves is a gigantic unit. The IB has so much stuff in waves. So this is really like a big overview of just the things that are in waves and like an idea or two from each one. Hopefully you use this to kind of help you remember the main ideas and dig in a little deeper to do some studying of your own. But here we go, an overview of waves. Okay, first thing, the thing that leads to a wave is simple harmonic motion. Remember, like a mass on a spring is not a wave, but it's an oscillating motion that is related to waves. So the one thing you want to remember about harmonic motion is this. This graph is the definition of simple harmonic motion. This is what will make a thing oscillate back and forth around an equilibrium point in a simple harmonic way. If acceleration is proportional to displacement and always directed towards equilibrium, right? That's what the negative means. If I'm got my little mass on a spring, it's displaced to the right, it's accelerating to the left, it's being pulled to the left, right? Remember, that means the net force is to the left. We call it a restoring force. And if the mass is to the left, it's being pulled to the right. And even more, the more it goes away from equilibrium, the more it gets pulled, which makes it goes a boinga, 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 and does simple harmonic motion, right? HL, you have a fun equation that, remember, this means something fun like the slope of this line is negative angular frequency squared. So fun, you might use it. Okay, but if you have a whole bunch of things oscillating, yeah, like a whole bunch of particles in a medium that are kind of vaguely connected and they can all oscillate up and down, well, a disturbance over here can make that energy travel through the medium. And all these little oscillations add up to make a wave. Okay, so the normal kind of traditional waves we talk about, or what you probably think of when you think of a wave, is a traveling wave. And a wave is really kind of energy. The idea of a wave is it's some energy goes through a medium and moves through it at a certain speed. Yeah, so a wave transfers energy. It does not transfer any stuff. The stuff in these, even look at this one, it's like an optical illusion. Pick any one of these dots, watch it for a minute. They don't really go anywhere. They go side to side, back and forth. But none of these particles are going from all the way on the left all the way on the right. Yeah, fun. Okay, remember the difference between longitudinal waves and transverse waves. These are the key words, parallel and perpendicular, right? Both of these waves are traveling left to right. Just like look at the big picture, see the waves moving left to right. Okay, but in the longitudinal wave, the particles also are, vibrating, oscillating left to right. In a transverse wave, they're going up and down. For this one, think of sound. For this one, light is a good one. Wave on a string is a good one. Doing the wave at a stadium is a good one. Okay. Light is especially, though, a good transverse wave to know because it's so much fun stuff in physics has to do with light, because light is an electromagnetic wave. Remember, this is what's waving in an EM wave. It's at the electric field and the magnetic field. Because of fun kind of right-hand rule style math, they're always perpendicular to each other. So the E field and the B field look like this in light. You do want to know the EM spectrum. Speaking of light, so you want to know the order of these, let's call them 7 different regions. Group radio all is 1. But memorize the order of these. Memorize that light is 10 to the minus 7 meters for visible light. That's the wavelength. They sometimes just want you to know that. And you want to know blue is over here, red is over here. So red's got a longer wavelength, lower frequency. Blue's got a shorter wavelength, higher frequency. All right, so just memorize. Make sure you have that stuff memorized. Also, key foundational waves thing is the wave equation. Yeah, and whoopsie, an easy one. Hopefully one that you are or get by the exams very comfortable with. Yeah, it's just the speed of a wave and how it relates to frequency and wavelength. This kind of tells us too, fun for constant wave speed, like something like blue light and red light, which both travel at the speed of light. Yeah, we have an inverse relationship between wavelength and frequency. So this kind of shows you long wavelength means low frequency, short wavelength means high frequency. And don't forget, I think this is officially in the simple harmonic motion unit, but the relationship between period, capital T here is period, and the time it takes for one cycle in seconds, and frequency. Okay, they're reciprocals. So yeah, you use these a whole lot. This is like most wave problems, maybe not most, but a ton of wave problems. This is like the foundational stuff you kind of build on. And definitely make sure you know the difference between wavelength and period. They're totally different things. Yeah, wavelength is the distance in, meters or centimeters or whatever between the peaks of a wave, and period is the amount of time it takes for a wave to, really a particle in the medium of a wave to complete one cycle of oscillation. Yeah, but it's the time it takes for a cycle. Okay. All right, here's some other ones. There's intensity stuff in 4.3. These tell you about the properties of a wave that affect its intensity. Topic 8 has the definition of intensity, so you can kind of jump around with this stuff, but that would be power over area. And maybe the key word to think of about intensity is received, because it's about what you see or hear or receive from a wave source. This doesn't really have to do, certainly it's related, that's this piece, amplitude, but it doesn't have to do as much with the thing making the wave as intensity is really a measure of what you're receiving. Okay, so the things that affect that are the amplitude of the wave and how far away you are from the source of the wave. Okay, so these are showing you intensity depends on amplitude squared. So you have two waves, one's double the amplitude of the other. That one will be will deliver 4 times the intensity. Yeah, because squared. And this is our good old inverse square law. It shows up all over the place. Make sure you understand how inverse square laws work. But, you got a speaker, make a noise. It's a certain loudness. If you walk 2 times further away, it should be 4 times less intense, as measured at least in watts per square meter, which is what intensity is. Okay, brightness for light, loudness for sound are good concept ideas to think about what intensity means. There's another intensity equation that you only use if you have polarized light going into a polarizer, aka an analyzer. You only use that equation if that's happening. I think we'll go over that in a second. Okay, 3 confusing terms that are very easy to mix up are diffraction, refraction, and reflection. And I had to tell you or remind you that those are 3 different things. So you want to know the difference. Diffraction is this. It's the spreading out of a wave when it goes through an opening or around a barrier. So you're sitting behind a pillar at a concert. You can't see anything, but you can still hear because the sound waves are the right size to diffract and spread around that barrier. But light is way too short. But if light goes through like a really narrow slit, you do see it diffract and make a diffraction pattern. Yeah, so this is kind of a good rule to keep in mind, as well as the idea of what diffraction is. If the wavelength of the wave is about the size of the opening of the barrier, like order of magnitude-ish similar, you'll see a noticeable diffraction effect. Okay, refraction and reflection, you want to have the kind of Snell's law picture in your head. This is when we're talking about light, or really any wave moving, but usually light, moving from one medium into another medium. So a common example is light shining from the air into a piece of glass. Something like that makes your straw look weird and bent inside of the glass, the part that's underwater. Yeah, but so refraction is the light that goes through. So we got light shining into a piece of glass or something here. This piece is the refracted ray. This piece is the reflected ray. Yeah, some of it will reflect. Reflection is easy. It just reflects at the same angle it came in at. All of these angles, remember, are measured relative to the normal, this line, perpendicular to the boundary between our 2 media. Fun. And anyway, all this stuff is dictated by Snell's law from good old our friend Willebrod Snellius, who came up with this. A bunch of proportions, so you use what you need. Watch the 1s and 2s. So n is the refractive index of the material. The one to memorize is that for air, n equals 1. That's really a vacuum. Air is close enough to a vacuum. We're not dealing with enough decimals to worry about it. So use 1 for n for air. If you got an air problem, otherwise they'll have to tell you, or maybe you figure it out. But it goes, n1 over n2, and then sine theta 2 over sine theta 1, and v2 over v1. So just be careful. It's easy to flip these the wrong way. Yeah, and again, these are all measured relative to the normal. The way the IB does it here is we usually call it 1 and 2. So 1 is the material you're incident from, and 2 is the material you're refracting into. Yeah, so that's the angle of refraction, the angle of incidence, the speed in the second medium, the speed in the first medium. If it's air or vacuum, you just use the speed of light. So if it's light, yeah. And there is one specific thing that you do want to remember that comes up fairly often, which is this critical angle thing. It's like a special Snell's law that happens, and it causes total internal reflection. Okay, if you see critical angle or total internal reflection, or any kind of hint that light is not making it out, you do this. You, long story short, make the refracted angle theta 2 equal 90. So this whole thing becomes 1 sine of 90. Okay, the reason is it's very specific, but when you're going from, let's see, a higher refractive index material into a lower refractive index material, like say I got light shining through glass that goes back out into the air, well, it'll bend away from the normal. That's the rule. When light slows down, it bends towards the normal line, but when it speeds up, it bends away. Well, if it bends away, we could maybe have a case where the angle of refraction would be 90 degrees. And just picture what that looks like. If you refract at 90 degrees, you're not going into the second medium at all. You stay within, right? That's the critical angle. That's the cutoff. And any steeper angle, nothing will refract, and so it will only reflect. And so that's why you get total internal reflection. Okay, so if that concept helps at all, but really you just want to kind of memorize critical angle, total internal reflection, theta 2 equals 90. See what you can kind of do from there. That's to find the critical angle. Okay, this here is a pretty common problem because it's got a lot of good polarizer concepts baked into one kind of quick little thing. But anyway, polarizers are all about Malice's law. So polarization is really just describing which way the E field in an EM wave is going. Most sources of light put out unpolarized light. The sun, light bulbs, stuff like that. It's a whole bunch of, we could say light waves stacked together, or photons or something fun. But it's a whole bunch of all the light. There's like pieces of the light where the E field's going this way, and pieces where it's going this way, and pieces where it's going this way. It doesn't care. It's going all over the place. You got unpolarized light with the E field all randomly waving about. But a polarizer will like absorb, say, the left and right oscillations and only let through the up and down oscillations, for example. So let's through half. All right, so the thing you want to know is you don't touch Malice's law if you're dealing with unpolarized light. When unpolarized light goes through a polarizer, it just gets cut in half. The intensity does. Yeah, so it looks like this. But when the light going into a polarizer is polarized, then you deal with Malice's law. Picture if I got light coming in this way, if this axis was straight up and down, it would let everything through. If this axis was side to side, it would let nothing through. And if the axis was in between, it would let this much through. All right, so this is Malice's law. The trick, and this isn't always the case, so don't like memorize this as this is the thing, but the trick is often what's coming in has been like messed with already, like back here. But okay, in this equation, this is the equation used if polarized light is going into a polarizer. And to make it more confusing, we sometimes call it an analyzer in that case. But analyzer, polarizer, basically same thing. Really same thing, we just, the context is different. Okay, but if polarized light is going in, then you use this equation. IO is the intensity of the polarized light going into the polarizer / analyzer. Okay, and then theta is officially the angle between the plane of polarization of the light and the transmission axis of the polarizer. So the light's up and down, the axis is like this. In the picture, your angle is yay big. Okay, you do the cosine of that angle squared, multiply by the intensity coming in. That tells you the intensity coming out. So in this classic problem, the light first gets cut in half because it's unpolarized, goes through, gets cut in half. And then what I do is the input in Malice's law is half of what I started with way back here. Yeah, so you do half and then you do cosine squared of the angle. But that's only because it was, cut in half back here. They don't always have this part in it. It doesn't have to be. You could just start with polarized light. It's just whatever's coming in right here, that's what goes in the, IO for Malice's law. All right, here's some other polarizer stuff you should probably study. Methods of polarization, like light bouncing off of a surface of water, and optically active substances like sugar water. If you send polarized light through sugar water, it will rotate the plane of polarization, like based on the concentration of the sugar water. It's so fun. Okay, moving on though. Some interference stuff pops up in topic 4. You want to know the basic idea of interference and how it works. This comes from superposition, which is a fun math thing that if you have two waves on top of each other, they will add together. And do be specific, the individual displacements of each wave add together, like at all points where they meet. Yeah, so you add two sine waves together. Like go to Desmos, add the sine of x to the sine of 2x. The sine wave that comes out, that's superposition. It's the addition of two waves. Okay, so if two waves meet, they'll superimpose. They'll do superposition. And so there's a lot of cases where we get two waves meeting, usually what we call two-source interference. The probably most classic one is the double slit. But you know, other common examples that we've done is like two water waves that meet and you get Ripley parts and still parts and Ripley part and still parts, or two speakers making a noise of a single frequency and you get loud spots and quiet spots. Yeah, those are points of constructive interference and destructive interference. Constructive interference, keyword is in phase. The two waves meet in phase. And destructive, they meet completely out of phase. All right, so it's all about path difference. Let's do these two examples real quick. So this guy's got constructive interference. I suppose, light because it's bright coming out of a slit down here and a slit down here. I'm going to look at 1 point, just 1 point on the screen over here. And I'm going to see that this wave went 1, 2, 3, 4.5 wavelengths to get there. This wave went 1, 2, 3, 4, 5.5 wavelengths to get there. Oh, well, what's the difference? The difference is one wavelength. This wave went one wavelength further than this wave. And just look at how waves work. That means they both meet up at the same point in their cycle. In this case, at the bottom, but the bottom doesn't matter. They're just synced up. So they're going to whoop, 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 whoop. Go like that together and add together and make a really bright spot with constructive interference because the path difference is one wavelength. All right. And over here is the opposite. This one goes, let's see, 1, 2, 3, 4.5. This one goes 1, 2, 3, 4, 5 full wavelengths. So notice this one's at the top of its cycle. This one's at the bottom. Like positive A plus negative A is going to give me 0. And the whole time that they're completely out of phase. They're 180 degrees or pi radians out of phase. So they'll completely cancel out and give us destructive interference because they were, you know, half a wavelength off. Or if they were 1.5 wavelengths off or 15.5 wavelengths off, that's the idea. All right, do watch out. Using your data booklet, your best friend can betray you right here because this is, I forget what it's called, but it's not called interference, this topic, 4.4. But this one is called interference, an HL1. These equations are only for thin film interference. If you pay attention to them, they're exactly the opposite of each other because of fun thin film stuff. Okay, so many IB students will get ruined by this equation because you flip through, you see a problem, it's like two speakers and there's interference. You're like, oh, interference, something about path difference or something. And you flip through and you see this and it says interference. You're like, oh boy, here we go. I'm going to do destructive interference. I'm going to set it equal to M wavelengths. That's exactly wrong. Yeah. So these are only for thin film interference. The one with the N and the M is only for thin films. Don't touch them unless the problem says thin film. Otherwise, you go to topic 4. These are your general, wonderful, friendly interference equations to use. Okay, the specific interference thing that happens a lot is the Young's double slit, or in general, this one is, I guess, a more general two-source interference pattern. It's almost always Young's double slit, but you can use this for like two speakers when the angles are small and all that good stuff. Okay, so this is the equation for two-source interference when you get like loud spot, quiet spot, or bright spot, dark spot, or water wavy, still water, water wavy, still water. Okay, this one's tricky because it's all distances. Like everything could be in meters or centimeters or whatever. So you just really have to study this and know. S is the distance between the bright spots, the maxima we call them, the loud spots, you know, the points of constructive interference or destructive. They're all evenly spaced. Okay, but there's a spacing between your maxima. If it's light, we call that the fringe spacing a lot. Lambda is the wavelength of the wave coming in. Capital D is the distance to your screen. Remember the setup where you have like a double slit and then a screen over here where you look at the pattern. So it's this distance. And little d is the distance between the sources, like the distance between your two slits or the distance between your two speakers. Okay, so they're all physical distances. This one's a little funky because this is an angle, so it should really be, you know, this would be a physical distance really on the screen. So that's maybe not the best graph in the world, but that's the idea. It's the distance between the bright spots. Okay. For HL, I guess for everybody, you do want to know the single slit diffraction pattern because when we're talking about light going through an opening, light will also do something fun, different than interference, kind of related in a weird way, but pretty much its own thing. It will also diffract because these slits can be small enough that you'll get a little bit of noticeable diffraction from the light. So the light will spread out, and for fun, weird reasons called Huygens principle, which is another fun one to maybe study a little bit. It's kind of crazy. You get like bright spots and dark spots still, even though there's only one slit. So anywho, there you want to know the general pattern that there's a really bright central maxima that's like double the width of the other ones because of fun geometry. And it's got these secondary and, further maxima, bright spots, but they're way dimmer, like a lot dimmer. Yeah. So that's a general pattern that you get, and this is the equation in HL. You want to know this is the angle in the equation. It's the angle to the first dark spot because math. Sometimes you got to find like the width of the bright spot or something, so use some trig. Always think about what you're looking at, draw it out, picture it. It's going to be a little different every time, but that's what the equation means, and B is the width of the slit. Okay, and every physics teacher's favorite is Young's double slit, and especially the IB's favorite because it combines both two-source interference and single slit diffraction. Yeah, so here's the diffraction pattern with our graph of intensity over position. Again, when you look at these graphs so much, you start to think this is what the thing looks like, but this is just a graph of how bright it is, right? Okay, so this is how bright it is over distance. This is how bright like a double slit is over distance without the diffraction. Well, what happens is the superposition of both of them, right? They add together, basically. Really, it's more like the double slit pattern gets squashed down to fit inside of the single slit pattern. They sometimes call it the single slit envelope. It envelops the max-min that you get from two-source interference. Okay, so basically you want to know that the interior peaks come from two-source interference. So like this distance between two of the closer together peaks would be S if I'm talking a physical distance. Yeah, that fit inside of the single slit pattern. And so now I got to change it up a little bit. If I was talking about an angle from here to here, right from the middle to this point, this is the diffraction minimum. That would be the theta in the single slit equation. So this is a great one to really study. Honestly, in general, if you're only studying a couple waves things, definitely make Young's double slit one of them. There's always problems on it. This like crazy pattern is good. There's so much good wave stuff in here. It gets pretty deep. So this is a good one to kind of study. Definitely at least know this pattern and, try your best with the difference between the interference pattern and the diffraction pattern and how they combine. Okay. Another interferency thing is the diffraction grating. This is like many slits. So we got one slit, we got two slits. You can have like thousands of slits. These are made to spread light out at big angles. So, oopsies. Okay, so this is the equation usually you want to use for diffraction gratings. You can honestly officially use this for like the double slit. The derivation is the same, but in double slit, we do a fun small angle approximation, which kind of makes this simpler. Diffraction grating spreads things out by really big angles though, so you definitely can't do that for a diffraction grating. So basically, if they say diffraction grating, probably come here. Let's see, n is the order of the diffraction, so we say like the stuff that goes straight through, when n equals 0, theta 0, it just goes straight through. So if it's white light, it's still white light here. But for like n equals 1 and n equals 2, the first order diffraction, the light will be spread out at different angles based on its wavelength. So red light, which has a long wavelength, will get diffracted at a large angle. So the red light gets pushed like, well, not pushed, spread way over here. And the blue violet light gets pushed, spread not so far. And you get to disperse your light. Yeah, you get to see all the component colors that make up light. And so you see the rainbows and any other light that's coming through. These are really useful for like emission spectra and absorption spectra, right? You point a diffraction grating at a star and see like what you see in terms of emission and absorption lines. It spreads them out nice and far so you can see what's what and be like, hey, that star's got some helium in it. Yeah. Okay, so probably use that equation if they say diffraction gratings. Okay, and the last of like the core stuff is standing waves. Standing waves is one to definitely study because the data booklet gives you no help for standing waves. Most of this stuff, if you really know the data booklet super well, you can make your way through certainly enough of the exam to pass and probably to do quite well. Standing waves, though, they give you nothing. You got to know some stuff about standing waves. You're really just applying like the wave equation, but in a tricky way. Okay. Here's some things about traveling waves and standing waves. You want to know the difference? I'll ask you to outline them. So know those. The points on standing waves that stay still are called nodes. The particles at these points never have any displacement at all. The particles at the antinodes have a really big displacement, so amplitude. Yeah, and everything in between. So you get this fun thing going on. These are formed when like two waves move through each other in opposite directions, something crazy like that. All right, and what you really want, and we're going to have to math through, is all of this fun harmonic stuff. So there's really kind of two cases, almost always. You can have a string fixed at both ends / pipe open at both ends, which are really the same math. The setup's a little different, but they're basically the same thing. They both, what we do to figure this out is you look at the simplest shape you can fit. And there's boundary conditions for all of these. The boundary condition, like for a fixed end on a string, is that it's a node. It's got to be a fixed end, like, you know, tied to the wall or something, or it's like a string instrument where the string is fixed both places and you pluck it and it vibrates. Right? Or you've got like an open tube, and, you know, blow some air across it or something, will make a noise. And the case for an open tube is the open ends are antinodes. The air is like going crazy at the open ends. Okay, but in both cases, because I got a node and a node, I have to have an antinode in between, or I have an antinode and an antinode, and I have to have a node in between. You get half a wavelength. So the length of the string / pipe is half of a wavelength, if you can picture that. Like this one's good. It's showing you what one whole wavelength would look like. And so using the wave equation and doing some algebra, you can get to here. This is the frequency of the first harmonic, the simplest shape I can fit, because I could do a node, antinode, node, antinode, node here, and continue and continue, get more and more of these little humps. Yeah, but that's the frequency of the first harmonic of those things. Do the same thing for a pipe closed at one end, but it needs a node here and an antinode here. That's good enough. That's a quarter of a wavelength, so the equation works out different. Okay. For higher harmonics, because you're not always dealing with the first harmonic, this is just like your base math that you deal with. The definition really is that the like nth harmonic is n times the fundamental frequency. The frequency of the nth harmonic is. So if you want to find the frequency of a fifth harmonic, you do one of these for the fundamental and multiply it by 5. All right. So that's a quick overview. There's a lot of standing wave stuff you can kind of study and look more at how this math works. But if you can draw these shapes and come up with these equations, or even memorize these equations, that'll usually get you there, at least get you started with the standing wave stuff. Just kind of do your best to draw the shapes and picture what's going on when you see a standing wave like this. Because again, you're really using this. You just got to be creative about thinking about wavelength. Okay, now on to HL stuff. There's a couple things in HL probably worth talking about. One is resolution. Resolution can be kind of tricky, but it's this idea of if you got two different images, two different sources of light, it's like an imaging system. Like common ones are your eyeball, or a camera, or a telescope, which all have openings that are circles, circular openings. That's an assumption we're going to make about the system we're looking at. But you get yourself a circular opening, light goes through the circular opening, it's going to diffract. Yeah, so it spreads out. It doesn't make like a perfect point on like the back of your retina. And if those 2 points are too close together, well, the two, like, you know, diffraction patterns will overlap in a way that you really can't tell that there's like a dip in between them, you know, of brightness. So these two images would be too close together. This is, again, the intensity graph. But these two images would be too close together. You would just see one kind of bright light. These two are definitely far apart enough that you could tell that it's two things. And this right here is going to be what we define as the cutoff, where you can just barely start to resolve these as two separate images. Okay, it's the mathematical cutoff of like when you could conceivably, possibly in a perfect imaging system, tell the difference. Okay. All right, so the rule for that is called the Rayleigh criterion. It's super specific, but basically the rule is the peak of one of these patterns has to be on top of the first zero of the other, and so vice versa. Yeah, so kind of just memorize that. It's called just resolved. It's just at the point where you can resolve the two images. If they're further apart, you can resolve them. If they're closer together, you can't. And if it's right on, you say they're just resolved. It's at the cutoff point. The equation in the data booklet is, I'm putting a little r there to call it the Rayleigh angle, but they just say theta. And you just got to know, it just says resolution, and this is the equation. You got to know this is the minimum. This is the angle that goes with the Rayleigh criterion. This is the minimum angle that the thing could resolve, the minimum resolvable angle. So it just depends on the wavelength of light coming in and the system, right? Like the telescope or the camera or the size of your pupil. So you put the size of the aperture, the diameter. Okay, it's similar to the single slit equation. You just get this fun 1.22 because that's like something when you have a circular opening instead of a slit. Fun fact, but there you go. It's in the data booklet like that. So that's what you do. That tells you the minimum angle. You'll then have to compare to an actual angle, usually, for these problems, right? Because they're going to say, like, the car is coming towards you and there's two headlights. Can you tell that they're two headlights, or do you think it's maybe a motorcycle? Yeah, so based on like the size of your pupil or whatever they give you, and let's do this, and the wavelength of the light coming in, right, which sometimes you'll do like an average thing, you figure out what the minimum angle that you could possibly resolve is, and then you compare. So this is a little thing you can do. It's really just doing right triangles and some small angle tricks. But basically, you got a thing like this, right? So here's you, here's the two headlights or whatever. This would be the actual angle, right? The actual angular separation of the two objects is all you're trying to figure out. So if that equation looks weird, it kind of is. You just do a little, this is one kind of way to do it, but you do like a little right triangle, because I'm going to have to split this in half to make a right triangle. You could probably do some other fun math. But let's see, this angle would be half of the angle we're talking about, the actual angle. And this would be half of the distance between the sources. So like the quick way to do this would be, I could do a tangent. Let's say I really want that guy, right? But remember, for small angles, which these definitely are, we're talking way less than a degree for all these problems. This is going to be the tangent of the angle, the side of the angle, basically all the same thing as long as we're in radians. So I'm going to do the angle and the tangent of the angle are the same thing. It's equal to opposite over adjacent. So the opposite side was d over 2. The adjacent, we'll call this capital D. The distance like from you to the car with the headlights or whatever. Yeah, and so you get this equation that the angle is the separation over the distance to them. All right, so if that helps, it kind of saves you some time to do this little approximation, but whatever method you come up with, this is a good one to kind of know, but you just find the angular separation between the two images, compare it to this. If it's bigger, it's resolved. If it's smaller, it's not resolved. Okay, moving on, simple harmonic motion. There's a lot of equations to simple harmonic motion. This is where you go if you're doing any math really with simple harmonic motion. This is the most important one. This equation is in every single one of these, even the pendulum and mass spring, I would say. Look at that period in 2 pi. Huh? Yeah, but that's angular frequency. It's like how, radians per second, how quickly you're going through your cycles for an oscillator. These two, it's good to kind of know what they're doing. If you know your calculus, you maybe can see what's happening here now, but they're doing calculus for you because this is not a calculus-based course. So you don't need to know it. But if you're comfortable with calculus, hopefully this makes sense. But if not, you just want to know the left two equations go together, the right two equations go together. So they're kind of saying the x is what you want to think about for your starting condition. So x is displacement. X sub 0 is amplitude. That's a weird like notation, but x sub 0 stands for the amplitude of the, oscillation. That's like the maximum displacement. So that's a set value for an oscillator. Okay, but so like if you start at the top of the motion and then you're going down and up and down and up, that would be a cosine graph for your position because you started at a maximum. And if your displacement is a cosine function, graph it out and do slopes of tangent lines or do a derivative and you get this. Yeah, your velocity would be a negative sine function and fun chain rule stuff happens. Whereas if you start at 0, and they'll always give it to you starting at 0 going up because they only give you these equations. If you start at 0, then your position is a sine function. You start at 0, go up. Then your velocity would be a cosine function. So just know you go from here to here or here to here, depending on if you start at 0 or start at a max. All right. And yeah, this has a period and a 2 pi. This is defined by a period and 2 pi. So often you're going to do some fun algebra between these. Sometimes you need potential energy. So do total minus kinetic, and there you go. You can get potential energy from these. So much fun math you can have with simple harmonic motion. Thin films, like we said before, are deadly. Thin films are very, very, very dangerous. Somebody's going to screw this up. A percentage of students will always screw this up because it's a trap. They really try to trap you, I feel like, with this data booklet. Yeah, it's so confusing. But again, like you go to the two-source interference problem, you're like, oh, interference section, let me use these. No, don't use these. These are only for thin films. Okay? But if you do have a thin film problem, like the problem literally says thin film of oil or something, then you go here. You only go here. Okay, quickly, it's this idea that light comes in. Part of the light will refract into my thin film. Like I've got a thin film of oil, you know, on top, floating on top of a water surface. It looks all shiny and rainbowy and stuff. Okay, so light comes in. Part of it will refract, but part of it will reflect. So I got one reflected right here. And then that light goes through, and there's another boundary right here, pretty close. Part of this will also refract. We just don't really care about that. And part of this beam will also reflect, come up back through. And I end up with two different rays that are able to interfere with each other. Okay, so it's this ray and this ray that'll interfere. And they interfere because they can, like the second one goes this much further than the first one. These are always drawn at angles so we can see what's happening. But we, for the IB, thankfully, they at least do this, because these do get even hairier when there's angles. It's really the light is coming straight down, and so part of it's bouncing up and part of it's going down and then back and then coming back up. So the path difference basically just ends up being 2 times d with this fun refractive index thing thrown in there for like an optical path difference or some craziness. All right, so anyway, the equation gives you what you need. Just be careful. N is the refractive index here, where everywhere else in the topic 9 stuff and a lot of this stuff, N is like the order of diffraction or whatever, right? Well, it's not. Now, M is like the order kind of thing of 0, 1, 2, whatever. N is your refractive index. There's your wavelength. All right, so anyway, watch out for that stuff. I guess we should mention, too, that this assumes you go from like low to high to medium refractive index, like this situation. So the rule that this ray gets phase shifted, but this ray does not applies, because if you reflect off something with a higher refractive index, there's a phase shift of pi radians. But if you reflect off something with a lower refractive index, there's no phase shift. Oh boy, thin films are hard. Be careful with thin films. If you see thin films, go to these equations, try your best. Okay, last, our favorite, the Doppler effect. All right, so Doppler effects are fun. Have this picture in your head. Be thinking about what's happening with the Doppler effect. This is a pretty thinky one. And you just really picture the ambulance driving by, the car driving by, whatever. Yeah, the siren. Coming close, it's high. Going away, it's slow. Yeah, so use that experience. These two are for sound. There's your variables. These are pretty well labeled. You got yourself a source equation with the sources moving, like our classic Doppler effect, like this. Ambulance drives by. Yeah, so I got the speed of the source. Or the moving observer. You run really fast at the ambulance. You'll hear a change in pitch too. That's your speed, the speed of the observer then. Okay. These are for light. They're the same as it's really the same as the Astro equation. Our Astro work helps us out there. But yeah, speed of light, speed of the thing. If we're dealing with Astro, it's like probably the recessional speed of a galaxy or something fun. But yeah, Doppler effect for light there. The main thing with these is the plus or minus. You have to pick, and you can memorize these, but don't, because they're backwards from each other and it's confusing. Just think about it. Think about the math. Okay, because like, okay, picture the moving source. If the ambulance is coming towards us, we know the pitch is high. And to make the pitch high, that would mean F prime is bigger than F. Well, what would I do here? I would subtract. Yeah, make the denominator small, the numerator bigger. So F prime would be scaled up. But if the ambulance then drives away from me and I hear the pitch get lower, then I know this has to be a fraction less than 1, so I would add down here. Okay, and flip-flop the rules here. Same reason. You run towards the ambulance, you hear a higher pitch, so you would add here. You run away from the ambulance, you hear a lower pitch, so you would subtract here. Okay. All right. So there you go. There's the big waves ideas, at least. So like I said, that's a very quick overview of some of the really big ideas of waves. Maybe not very quick, but waves is a lot. Okay, so use this as a starting point to hopefully find some wave stuff that you can study and practice. That's the most important thing. Do some practice on these. Try to apply those ideas. Dig into some of these concepts a little deeper. And do what you can. Get what you can on the IB exams. All right, and have some fun. Good luck.